Hey everybody, welcome back. So far in calculus, we've learned how to compute derivatives by the definition. The limit as delta x goes to 0, ... And we've come up with some rules and properties of derivatives. The power rule, for example, the derivative of a constant times a function. The derivative of a sum or difference equals the sum or difference of the derivatives of sine and cosine. So we've learned how to compute pretty much by inspection the derivatives of polynomials plus things like square roots, cube roots, and so forth, and certain combinations of sines and cosines. For the purpose of being able to broaden those functions whose derivatives we can compute pretty much by inspection, or if not by inspection, without too much work and without resorting to the delta x method of computing a derivative, we're going to look at the derivative of a product. And we know that when we compute the derivative of the sum or difference of terms, we compute the derivative one term at a time. The derivative of a sum or difference, let's see, f of x plus or minus g of x. The derivative of a sum or difference is equal to the sum or difference of the derivatives. So in other words, if we have the derivative of a sum or difference, we compute the derivative of the first term, and we compute the derivative of the second term, and so forth. So it would be a reasonable conjecture for us to say that if we have the derivative of a product, then the way we compute the derivative of a product is we compute the derivative of the first factor, then compute the derivative of the second factor, and just multiply them together. And pretty much do it this way. So it seems reasonable, and this would be completely consistent with what we've done so far. Just for the sake of being thorough, though, let's just make sure that this really does work. We're going to verify the truthfulness of this conjecture, and then we'll go on from there. Okay, this is what we're out to establish. The conjecture that if we compute the derivative of the product of two functions, the way we do it is we compute the derivative of the first and the derivative of the second, and just multiply them together. But until we establish this, let me put a question mark over this equal sign. And we'll keep the question mark here until we've actually established that this relationship really does work. And I guess maybe something that we should do is just come up with some kind of a test case. So let's do that. Test case. And let's just pick a couple of things whose derivatives are fairly simple. Let's say this is our first function, x cubed, and x to the fourth is our second function. And if this relationship works, which we're pretty sure it does, then really we should be able to compute the derivative of the first function and the derivative of the second function. And it should work. So let's see, the derivative of the first function, the power rule tells us bring the exponent down front and then subtract 1 from the exponent. And here, bring the exponent down front and subtract 1 from the exponent. Now multiplication's commutative and associative, so 3x squared, 4x cubed, there's 4 factors there. We can reorder these factors any way that we want and multiply them together. So let's take the constants. 3 times 4, that's 12. And then take x squared and x cubed. We have x to a power and x to a power. What do the exponents do? They add, right? So x to the second, x to the power of 2 plus 3, that's x to the fifth. Okay. Now again, just for the moment, I'm going to put a question mark over here until we actually do verify that this thing is equal to that thing. So I'll put a question mark over the equal sign until we've actually verified this conjecture. I guess the question is, how do we verify the conjecture? Maybe if we can compute the derivative of this expression, but do it a different way. We'll do it a way that we already know works, okay? We can start right off, let's see, x cubed times x to the fourth x cubed times x to the fourth. We can combine these two factors into one factor. It's x to a power times x to a power. The exponents add, don't they? So this is going to be x to the seventh. And we know how to compute this. This is just the power rule. Bring the exponent down front and then subtract 1 from the exponent. Now the thing is, we know that this is right because we know that x cubed times x to the fourth is x to the seventh. And we know that the derivative of x to the seventh is 7x to the sixth. So we know that this is right. Oh, but look, we compare the answer that we get using this method with the answer that we get using the other method. They're not the same answer. And since we know that this answer is correct, we also have to know that this answer is not correct. Ooh, that's a big oops. Well, you know, when a plane falls out of the sky and crashes, they have a bunch of investigators gather all the parts of the plane and reassemble them and try to figure out what went wrong to make sure that what went wrong never ever happens again. Let's do that with this example. Something went wrong here. Let's figure out what it was. Now, 3 times 4 equals 12. Well, that's right. And x squared times x cubed, the exponents add, so we get x to the fifth. Going from here to here, we know we did that right. So let's back up. Derivative of x cubed, is that 3x squared? Yeah. Derivative of x to the fourth, is that 4x cubed? Yeah. So we didn't make any mistake going from here to here, and we didn't make any mistake going from here to here. The problem had to be going from here to here. We assumed that if we compute the derivative of a product, that we can compute the derivative of each factor and multiply them together. And you know what? It didn't work. So I guess it's a good thing that we put this question mark over the equal sign after all. This does not work. So today we're going to beat to death, and I say that with a smile on my face, but I'm very sincere also. I do intend to beat this to death. But we're going to beat this to death, but we're also going to look at how we do or how we compute the derivative of a product correctly. And in my own personal way, I'm going to beat that to death too. Okay. We've established that we can't compute the derivative of a product by computing the derivative of each factor and then just multiplying them together. And please allow me the satisfaction of beating this horse to death and beating this horse to death so long that it never, ever, ever has a chance to come back to life. This does not work. We can't compute the derivative of the product of functions by computing the derivative of the first function times the derivative of the second function and multiplying them together. It doesn't work. And yet, it seemed like a reasonable thing to do. The analogous thing, when we computed the derivative of the sum or difference of functions, worked. When we had the derivative of the sum or difference, we'd compute the derivative of the first term, and then the derivative of the second term, and then the derivative of the third term, and so forth, and just add them all together. For sums and differences, it worked. But for products, it doesn't work. And so I'm going to write out, which would be the intuitive thing to do, the derivative of a product is the product of each of the derivatives. But it doesn't work. So the common sense thing to do when we compute the derivative of a product turns out not to be right. And so I emphasize, no, don't do this. It doesn't work. We can't compute the derivative of a product by computing the derivative of the first factor and the derivative of the second factor and so on and multiplying them together. It doesn't work. And I'm beating this to death because this seems like a very reasonable thing to do. It really does. It makes sense. But it doesn't work. And because it seems like such a reasonable thing to do, I'm really emphasizing that, hey, I know it seems reasonable that these two things should be equal, but they're not. So let's not make this mistake. And now, to be fair, since I've spent so much time explaining how not to compute the derivative of a product, it's only fair that I tell you how we should compute the derivative of a product. I should explain and beat to death how it is that we compute the derivative of a product. Everybody, this is how we compute the derivative of the product of two functions. And I'll tell you what, this is not at all intuitive. I would never in a million years guess that this is what the derivative of the product of two functions looks like. We have a name for this because it is not intuitive and because it corrects what would be a false but intuitively obvious notion that we can compute the derivative of a product by computing the derivative of each factor and multiplying them together. Since this corrects an intuitively obvious but false notion, we have a special name for it. It's a rule, and it's a rule that we memorize. We call this the product rule, and here it is. It tells us how to compute the derivative of the product of two functions. And let me take this rule and sort of diagram the rule just to make it easier to memorize. Okay, here's how we diagram the derivative of a product. We have two factors, f of x and g of x. So we'll call f of x the first factor, g of x the second factor. And this is what the derivative turns out to be. First prime, the derivative of the first factor, times the second factor, plus g prime of x, the derivative of the second factor, times f of x the first. First prime times second, plus second prime times first. And I've written it down here. This is, I guess you'd call it a mnemonic device for memorizing the product rule. And it always helps if we have a rule that has a little bit of rhythm and rhyme to it. It's invaluable to remembering. For example, what letter comes after H in the alphabet? If you're like me, you'll probably go A, B, C, D, E, F, G, H, I. I. Well, we have a song, the alphabet song. And sometimes when we get stuck and think, well, wait a minute, what comes after H? Let's see, A, B, C, D, E, F, G, H, I. Okay. We have a mnemonic device, the alphabet song, to help us remember the letters of the alphabet. To help us remember how to compute the derivative of a product, we have the product rule. First prime times second plus second prime times first. First prime times second plus second prime times first. First prime times second plus second prime times first. First prime times second plus second prime times first. Now, if we say that about 5 or 10 times a day for the next 3 days, we'll know it for life. And we will always remember how to compute the derivative of a product. And believe me, I wasn't always a good student. But when I finally became a good student, I looked for any advantage that I could get to help me do well in the course. And I had calculus 3 times. I had it in high school. Then I had it again in technical college. I wasn't a good student at that time. About 6 or 8 years later, I decided, when I went back to school, I decided that I was going to be a good student. And I became a good student. And this is one of the things that I did. Anything that would give me any advantage, I grabbed onto it, and I wouldn't let go. And this was one of them. So did I walk around campus for a few days going first prime times second plus second prime times first, first prime times second plus second prime times first? You bet I did. And there may have been a few people who had thought that I'd lost my mind. And I won't say that they were completely wrong, but the end result is I got an A in the course, and I actually understood math for the first time in my life. I decided to play by the rules, do all the work, memorize the things that I was supposed to memorize, and I was shocked that I was actually understanding math. So when I finally became a good student, and I wasn't always a good student, but when I finally became a good student, this was the type of thing that I did. And this was one of those things that I actually did do. I walked around and I said, first prime times second plus second prime times first prime times second plus second prime times first. And you know, when I did my homework, I didn't have to look back in the book to find out how to compute the derivative of a product. I just looked at it and said, oh, it's a product. First prime times second plus second prime times first. And the problem was pretty much done for me already by that point. So I'll get off my soapbox and we will do a ton of examples. You know, it only seems fitting that maybe for our first example using the product rule, we'll use the same example that we used for our test case just a couple minutes ago. And here's what I'm going to do. I'm going to make sure that I apply the product rule and apply it correctly. So I'll look at this x cubed here and I'll say this is my first function. And I'll look at x to the fourth and I'll say this is my second function. And then I say to myself, first prime times second plus second prime times first. Ah, I know what I'm supposed to get. First prime times the second plus second prime times the first. That's what the product rule tells me that I should get. And what I've done is I've pretty much made a template to fill in. All I have to do is plug in the right thing in each place, and I've got my answer. So, do we really need to go to all this trouble just to compute the derivative of a product? Well, maybe for a while we should. When I finally became a good student, I actually set things up like this just to make sure that I became a good student. I had finally gotten tired of failing in life, and I thought, okay, I'm going to grab every advantage I can get to make sure that I succeed. And it was one of the few wise things I had ever done in my life up to that point. But we have the template laid out just the way the product rule says it should be. So let's just fill in the blank. First prime, the derivative of the first function, power rule. Bring the exponent down front and then subtract 1 from the exponent. Okay. First prime times second. So what goes here? The second function verbatim, x to the fourth. Okay, now second prime, the derivative of the second function. It's a power rule problem. Bring the exponent down front and then subtract 1 from the exponent. So there's second prime. And what goes here? The first function verbatim, x cubed. Okay, now let's tidy this up a little bit. We have 3 And x squared times x to the fourth, the exponents add, so we get x to the sixth. And over here we have 4. And x cubed times x cubed, the exponents add, so we get x to the sixth. And we have like terms we can combine. 7x to the sixth. Okay. Well, we did a test case with this example before. Let's use this as a test case again to show that the product rule really does work, and it really does give us the derivative of a product. So I think what we did before was we said x cubed times x to the fourth. We can just combine that into one factor. The exponents add, so this is really x to the seventh. And then from there, we just compute the derivative of x to the seventh. It's a power rule problem. Bring the exponent down front, subtract 1 from the exponent. Oh, and look what happens here. Son of a gun. They're the same. So the same test case that we used before, we can use here to show that, at least with this example, the product rule really does work. And now you're probably asking yourselves, well, if we could compute this just by combining these two factors into one factor and using the power rule, then why do we need the product rule at all? Why can't we just combine the factors into one factor and use the power rule? And the answer is we can't always combine the factors into one factor, as our next example will show. Here's a case in point. We have a product of two functions, and there's no way that we can combine these two factors into one factor. The only way to compute the derivative of this thing is to use the product rule. So it's a good thing that we're going to be walking around for the next few days going first prime times second plus second prime times first prime times second plus second prime times first. Okay. So what I'm going to do is diagram the function that I'm computing the derivative of. Here's my first factor. Here's my second factor. And the product rule tells me first prime times second plus second prime times first. Okay, I can do that. Here's first prime, and here's second, plus second prime times the first. I've created a template. All I have to do is fill in the blanks. First prime, the derivative of x cubed. The power rule tells me that I should get what? 3x squared times the second function verbatim, so sine x, plus second prime, the derivative of the second function. What's the derivative of sine of x? See, this is something we'll have to memorize. Derivatives of sines and cosines we'll have to memorize. Derivative of sine of x is what? Cosine of x. So here's the second prime, cosine of x, times the first function verbatim, x cubed. And there we have it. This is our derivative. By the way, some of you may have taken calculus before, and if you have, you may have learned a slightly different version of the product rule, different but equivalent to this. If you want to use the version that you already know, that's fine with me, just as long as you've memorized it correctly. More exercises. Here we go. The derivative of another product. And again, this is a product whose factors can't really be combined into one term. At least I don't, factors can't be combined into one factor, excuse me. So we have to use the product rule. Here's our first factor, and here's our second. And we remember what the product rule says. What does it say? Have you got it memorized yet? First prime times second plus second prime times first. Okay, so I'm going to write that down. So here's first prime times the second plus the second prime times the first. I have a template all laid out. All I have to do now is fill in the blanks. What could be easier? First prime. So we want the derivative of the first function. And what's the derivative of sine of x? It's cosine of x, right? Okay. So we have cosine of x. And then we have the second function verbatim, cosine of x. And then we have second prime. So the derivative of the second function, let's see, what's the derivative of cosine of x? Do we have that memorized yet? It's negative sine of x, isn't it? So negative sine of x goes here. That's the second prime. And until just recently, we spelled prime P-R-I-M-E. Let's see, I guess even after I became a good student, my spelling didn't improve quite as much as I wanted. Okay, we have second prime times the first function verbatim. So here it is, sine of x. And I guess we can simplify this a little bit. If we were doing this on a test and we left it like this, I wouldn't have a problem with that. But we can simplify this. So it's cosine x times cosine x. So that's cosine squared x. And minus sine x times sine x is negative sine squared x. So this is the derivative of sine of x times cosine of x. Let's do one more example before we throw a few monkey wrenches into the gears. Okay, the derivative of a product. And you know, this is one where we could multiply everything together first, and then we really wouldn't have the derivative of a product. But you know what? I look at these two functions and I think, do I really want to multiply these out first? I don't know. I think I might rather slide down a 90-foot razor blade and land in a pool of alcohol rather than have to multiply these two things out. So I'm going to use the product rule. Here's my first function, and here's my second function. And I've been working on my product rule, so I know that the product rule says first prime times second plus second prime times first. Got it. Okay. First prime times second plus second prime times first. That's what the product rule tells me I should get. All I have to do now is fill in the blanks. First prime, that's the derivative of this function. Bring the exponent down front. We get 2 times 3, which is 6 times x to the first. So 6x, derivative of 6x, the derivative of a constant times x is just the constant. So derivative of 6x is just 6. Okay. There's my first prime. Times the second function verbatim. That's this thing, 8x squared plus 9x minus 7. Then we want the second prime, the derivative of the second function. So we get 2 times 8 is 16 times x to the first. The derivative of 9x is just the constant 9. And of course, the derivative of negative 7 is a constant, right? So its derivative is 0. And by the way, when I computed the derivative of this function, I should have mentioned that also. Derivative of 3x squared is 6x. Derivative of negative 6x is negative 6. And the derivative of 4, since it's a constant, is 0. So the derivative is just 6x minus 6. And the derivative of this, 16x minus 9. Oh, plus 9, I beg your pardon. So that brings us here. What we need to do to complete this is just write down the first function verbatim. 3x squared minus 6x plus 4. And we are done. Usually, I leave the answer in this form unless I have a really good reason to do otherwise. If we're told to simplify the answer, well, yeah, I'll simplify it. But if I don't have to simplify it, I don't. Okay, I'm about to throw a monkey wrench into the gears. Here's the first monkey wrench that I throw into the gears, so to speak. How do we compute the derivative of the product of three functions? Now, I'll admit we won't see it very often, but we will see it. Why is this so problematic? We've been computing the derivative of the product of two functions. So why should it be such a big deal to compute the derivative of the product of three functions? And if we think about it, the reason that this is problematic is that the product rule only tells us how to compute the derivative of the product of two functions. The product rule doesn't tell us how to compute the derivative of the product of any number of functions. The product rule only tells us how to compute the derivative of two functions. So you know what? Unless we can take this product right here and somehow analyze it as being the product of two functions, we're up a creek. So, how are we going to do this? I guess what we'll do is we'll call this the first function. And g of x times h of x, we'll call that the second function. If we look at it that way, then maybe we can do it. So we're looking at this now as the product of two functions. And the product rule tells us first prime times second plus second prime times first. Okay, I got it. I'm going to get first prime times second plus second prime times the first. I've written out my template. So maybe this is easier than I think it will be. First prime, that's the derivative of the first function, and that's f of x. Okay. Derivative of f of x is f prime of x. So far, so good. First prime times second, we take the second function verbatim and put it here. Here's the second function, g of x times h of x. Okay, plus the second prime, the derivative of the second function, and I said, oops, the second function's a product. Well, actually, that's not such a bad thing. The product rule tells us how to compute the derivative of the product of two functions. The only thing is, I'm right in the middle of doing the product rule, and I don't want to be doing the product rule on something else at the same time. So here's how I handle that, just to make sure that I'm not doing so many things at once I forget what it is I'm actually trying to do. I'm going to write myself a little sticky note. Now note, this expression, when we see it, we regard this entire expression as being the derivative of g of x times h of x. We haven't actually written out what that derivative is yet, but we do consider this expression to be the derivative of g of x times h of x. So technically this is second prime. And this is sort of a sticky note for me, a reminder that tells me after I get done with all of this, I need to take a second step and compute what this is explicitly. So this sticky note here tells me, hey, finish up what you're doing right now, and then add another step in which we actually write out what this thing is. So here's my second prime times the first f of x Okay. Now I just gotta compute that. So I have f prime of x times g of x times, that's a funny looking h, times h of x plus the derivative of this product. Well, what's it going to be? Here's first and here's second. So we should get first prime times the second plus second prime times the first. Okay, I just computed this derivative explicitly in terms of g's and h's and g primes and h primes. And I just got to make sure I don't forget this guy on the end here, times f of x. Now, just for the sake of trying to make a pattern emerge, I'm not going to leave the answer like this. I'm going to simplify it and see if anything jumps out at me. I'm going to simplify it and see if I have one of those OMG moments. This term I like so far. F prime of x, g of x, h of x. And now I have to distribute f of x to this term and to that term. And I think when I do, I'm going to put the f of x right in between here. So this will be g prime f of x, h of x. And you know what? I think when I distribute the f of x to this term, I'm going to do the same thing. I'm going to put the f of x in between h prime and g of x. And I'll tell you what, I like the form that I have this answer in. And so at the top of the board, I'm going to rewrite this. And I'll erase everything else below. But I'm going to rewrite this result at the top of the board. And we'll look at it and we'll analyze it. Here's our result. And we want to look for a pattern. And to help the pattern jump out, I'm going to call this first. I'll call that second. And I'll call that third. And I think I really do see a pattern emerging. Let's see. I have first prime times all the rest of the functions. I have second prime times everything else. I have third prime times everything else. So first prime times the rest of the functions. Second prime times the rest of the functions. Third prime times the rest of the functions. You know, I can remember that pattern. I definitely can. There's a pattern here. And usually when I teach this topic, I add the note right here. My note says, note the pattern. And you know, a lot of times in mathematics, pattern recognition really goes a long way. So this is a pattern that we should have memorized. The derivative of the product of three functions, first prime times everything else, plus second prime times everything else, plus third prime times everything else. That's how we compute the derivative of the product of three functions. Now, based on this, how would we compute the product? No, how would we compute the derivative of the product of four functions? Outside of Calculus I, I don't think we'll see it. If we do see the derivative of the product of four functions, it will be one of those things that we see once in a blue moon, so to speak. But just for the sake of really driving home the pattern, let's consider how we compute the derivative of the product of four functions. And I'm going to erase that just because I'm short on board space. Holy moly. We have the product of four functions. And I'll tell you how I think it's going to work out. I think it's going to work out just like this. First prime times everything else, plus second prime times everything else, plus third prime times everything else, plus fourth prime times everything else. And let me write that out. First prime times everything else, g of x, h of x, k of x. So here's my first prime times all of the other functions, everything else, plus second prime, that's g prime of x, times everything else. So that would be f of x, h of x, k of x, plus, let's see, here's my second prime, plus third prime, h prime of x, times everything else. So that's f of x, g of x, k of x, And then finally, fourth prime. So that's k prime of x times everything else. F of x, g of x, h of x. And again, with this one, I make the comment, note the pattern. And you know what? That pattern even holds for the derivative of the product of two functions. It's just that with two functions, it wasn't really obvious what that pattern would be, but I'll write it down anyway. Here's our first. Here's our second. And the product rule says we get first prime times the second plus second prime times the first. Now, how does that work out? It's first prime times everything else plus second prime times everything else. So that's actually the pattern that we use even for the derivative of the product of two functions. It's just that with two functions, it didn't really jump out at us. Now, let's say, we've discussed how to compute the derivative of the product of three functions or the product of four functions. But we haven't actually done an example, so I guess that's the next step. Okay, the derivative of the product of three functions, x cubed, sine of x, cosine of x. The first thing I'm going to do is just label these first, second, and third. And I'm supposed to get first prime times everything else. So here's the first function. First prime using the power rule. Bring the exponent down front. Subtract 1 from the exponent. So that's 3x squared. First prime times everything else. Sine of x, cosine of x. Plus second prime times everything else. Second function is sine of x. What's the derivative of sine of x? Cosine of x. So here's second prime, cosine of x, times everything else, first and third. So x cubed, and then the third function, cosine of x. And then finally, third prime times everything else. So the third prime is, let's see, derivative of cosine, what is that? Negative sine. So let's see, negative sine of x, there's my third prime, times everything else. So that's the first and second. So x cubed sine of x. And here, I guess I'd write it out just so that I could simplify having two different operators, plus and minus, next to one another. And maybe also so that I could get the polynomial out in front. Typically, we put polynomials first and trig functions second. So let's see, 3x squared sine x cosine of x plus x cubed cosine squared x, okay, plus x cubed negative sine squared. Now, I guess I could simplify this a little bit more with a trig identity, but I'm not going to. I'm going to leave it just like that. So that's how we do the derivative of the product of three functions. And I think I'll stop this lecture here and assign some homework. And then I'll do a lecture on the quotient rule. How about that? Okay.